I took data from every regional, national, and international VGC tournament to describe scientifically which VGC regulation was best. Okay, maybe not actually best, just had the most Pokemon. This figure is called a rarefaction curve. What we're going to do in this video is build up to an understanding of what the heck this thing means. We can think of an ecosystem as a collection of individuals that fall into discrete natural categories. Each category occurs at a specific frequency. Some are common, others are rare, depending on an underlying set of ecological rules that are generally hard to directly access. Real-world ecosystems can get very complicated very quickly. But no matter whether you're sampling from a Pokémon route, a real forest, or a VGC metagame, the same principles are at play and the same problems will probably arise. Which is why, in pursuit of understanding the rarefaction curve, we're going to begin in the grass outside New Barktown. For a route in a Pokemon game, it's very easy to look under the hood. If you walk in the grass, in the daytime, in Generation 4, you have a 55% chance of finding a Pidgey, a 40% chance of finding a Sentret, a 5% chance of finding a Rattata, and a 0% chance of finding a Hoothoot. They only come out at night. What we're going to do is do some ecological monitoring of Route 29, and through that process, see why rarefaction is such a useful technique. My first 10 Pokemon on Route 29 were 7 Pidgeys, 2 Sentrets, and a Rattata, which is interesting, because we'd expect to find 5.5 Pidgeys, 4 Sentrets, and half a Rattata. So we're overestimating Rattata and Pidgey, and we're underestimating Sentret. We still have vaguely the right picture. We've found all 3 of the Pokemon available, and they're in the right order. So we have the most Pidgeys and the least Rattata, but the actual proportions we found are a little bit out of whack. Let's increase our sample size to 25. And what we'll see is that the proportions of each species are starting to converge upon the true underlying values. But we're still overestimating Pidgey, we're still underestimating Sentret. Let's increase our sample size again, and what we'll see is that our estimates become pretty accurate. Our sample size is large enough that we'd be able to make basically correct claims about the proportion of Pidgey, Rattata, and Sentret in Route 29. But there's a problem. What do we do when there are individuals in the ecosystem that are so rare, so difficult to find, that we could run around 500 times, 5,000 times, and still never see them? In fact, that's the case even in this simple Pokemon route example, because they're a shiny Pokemon. If you think of shiny Pidgey, shiny Hoothoot, and shiny Rattata as unique individuals, imagine how many times we'd have to run around in the grass in order to find all of them. In fact, you can break it down even further, because these Pokemon can be male or female, and their levels can range from 2 to 4. So we could categorize 18 different unique wild encounters on this route. How many samples would we need to do to find all of them? But we don't have to worry, because that's what rarefaction is for. By rarefying our data, what we can do is extrapolate forward from the species, the Pokemon that we do see, to predict with some uncertainty how many we could see if we could do an endless number of samples. This is important because in a natural environment there are often a very, very large number of very, very rare individuals. Similarly, in a VGC tournament, there's quite a large number of Pokemon that you could win a regional championship with, but the teams that they're on are probably very, very niche, very specific, and any individual one of them is quite unlikely to get a placement. If we can use a rarefaction curve to make that prediction, then that saves us the effort of having to actually do the infinite sampling, which sounds pretty great, because even running around and finding 100 Pokemon was kind of mind-numbing. So an infinite number sounds really mind-numbing. Here's how I got my dataset. I went to the wonderful website Nimbaso City Post, where they post all the teams that are entered into every tournament, and I manually typed them all out into Excel, which took me a very, very long time. At the end of it, I had looked at 16 teams from 78 Pokemon tournaments, each of which had 6 Pokemon, giving me a sum total of 7,488 individual Pokemon observations. I have this enormous data sheet. If I can zoom out, see, it just keeps going and going and going until it crashes my computer. But it keeps going and going, and now it's broken. Hello, Excel? Oh no, you work. Then we plot that into RStudio. We can get our abundance counts, we can get our diversity counts, and then we can do our rarefication. To answer the question, what is the true number of Pokemon that can be found in each VGC metagame? These are our sample sizes for each regulation. Now there's quite a lot of variation here, just because some regulations had many more tournaments than others. A and D had the fewest. A was the initial regulation before they added the Paradox Pokemon, that only had a few regionals, and then D was the Worlds regulation for 2023, which didn't last very long after Worlds because Pokemon from the DLCs were made legal. Regulation I here also has a rather low sample size. That's because it's not finished yet. I've made this video in the middle of June, and as of now, there's still like half a dozen Regulation I tournaments to come. The keen-eyed among you will have noticed Q. What the heck is Q? Q is the second round of Regulation G. So G came and then it went and then it came back again. And I've counted them separately because I think it's interesting to look at whether the second time Regulation G came out, when it was more solved, when people had a better idea of what teams were good, if the diversity, the expected diversity cap, became lower as a result. Here is our diversity metric. This is the total number of unique Pokemon species we observed. And you'll see that it correlates with the previous figure because we're not scaling for sample size. So a regulation like F, which had over 1,200 observations, naturally also has quite a high number of Pokemon species observed within it. But it's not a perfect correlation. So if we look back at A and D, there were more teams used in Regulation D than in Regulation A. But Regulation A was significantly more diverse, even though the sample size was lower. So okay, that's kind of interesting. The rarefaction curves tell us the whole story. Now, the way to read it is we have sample size going along the bottom. That's the number of Pokemon we observed, the number of times you ran around on the grass and found a Centret or a Rattata. And then on the y-axis, going upwards, we have the number of unique Pokemon that we saw. Now, the way rarefying data works is we shuffle up all the observations and then we randomly remove them. This should smooth out our curves and give us a better view of what's really going on. The grey vertical line at about 200 observations represents the regulation with the lowest samples, in this case A, and reading off of that line gives us our diversity estimate. We can say with relative confidence that regulation G was the most diverse. Now, G was the single restricted. Regulation I is a dual restricted, you get to bring 2. G, you only got to bring 1, and had a significantly higher richness than all the others, including Q, which is also G, but it's G the second time. Abel, causing a ruckus. Sorry if there's any noise in the background from Abel just clattering around everywhere. So yeah, it turns out we do see a drop-off in diversity. As the metagame gets more established, people figure out what's good and what's bad. Looking down at the bottom, we can see that Regulation D has by far the lowest diversity. I suppose it was all Urshifu and Amoonguss and Incineroar. The important thing to remember, though, is that statistics don't tell a story by themselves. You need to have an interpreter. One reason I can think of why D would be so much lower is that looking at the top 16 teams of the World Championships is quite different to looking at the top 16 of the average regional. Because the tournament starts with so many more people, and because the people are the cream of the crop, those top 16 teams are going to be incredibly refined, which probably also means they're going to be more homogenous. They're going to be only the very best of the very best Pokemon. And so, with all of the niche off-meta picks pruned out over the course of the World Championship, Pokemon richness declines. Now, D is not the only regulation that a World Championship has been played in, but because it also has a low sample size, the number of observations that we've made that are from Worlds teams makes up a much larger proportion of the total pool of Pokemon available for Regulation D, and so it is the least healthy metagame, the least diverse metagame. Regulation C is also suffering. This is the one with just the Paldea decks, but you're allowed to bring Paradox Pokemon and you're allowed to bring Chi-Yu, Chien-Pao, Tinglu, and Wo-Chien. I guess that was potentially over-centralized by those very strong Pokemon that were allowed in. And then you can look at Regulation I. This is the current regulation. And it's middle of the pack. It's up there with B, the Fluttermane regulation, E, the DLC 1 regulation. Rather non-diverse so far, and if we found a real trend between G and Q, then we probably don't expect I to become more diverse over time. So yeah, that's the story of the rarefaction curve. What I'm really interested in is your analysis in the comments, because I'm not really a VGC player. You know, I do my share of following other VGC YouTubers, but you know, I'm a dirty singles player. Doubles is just too much for my little brain, you know. There's like four guys and they've got 4 buttons. It's too much. But I'm sure that there are some of you watching this who have dabbled in VGC. And I would love to hear your analysis of this figure in the comments. I should also say rarefaction is not some amazing, perfect statistical test. In fact, there's a decent argument to be made that it's not a good test at all, and that we should be using something more robust. I'm also very interested to hear your thoughts on the scientific validity of all this, because I suspect it might be actually slightly dubious. Thank you for watching. This has been a weird video. I'm in a state of mental delirium, but I appreciate everyone for watching. I'm going to try to keep making videos, but the Masters is really consuming me. And, whoa, Abel, you're, whoa, Jesus. Oh my God, Abel. That's my shelf. Abel, I need that stuff. Ay, ay, ay. He's knocked over all my board games and my kettle. The kettle is about to spill onto the floor with gross old water from 6 months ago. Yeah, you're a menace. You're a menace. That's cute, but it's going to be really annoying for the viewers because it's going to make a really loud noise. I'll have to mute it. Yeah, I know you've... Yeah, good work. Okay, well, we're going to say goodbye for now because Abel's demanding my attention. Oh, also, look at this cool thing I got. It's a pocket microscope. I can point it at things, and it microscopes them.